Okay, hello again. Welcome back. I do I realize I find myself like just sitting quietly for 10 minutes in between these recordings. I don't know. It's somehow mentally appropriate to just like for me to also just take the 10 minutes. It's fine. Okay. Um so the data you get is just not always the data you need. And the question is like, well, what's between me and where I need to be with it? And it can be a lot of stuff. Data cleaning, again, in general, very um, free form, I guess. Um, so there's very often judgment calls to be made here. And again, like back in this Jupyter notebook with the zip codes, it is very much a judgment call whether these non-New York City zip codes should be in the data set. And I don't think there's any answer to be given here. Or I mean, again, I don't know in detail what's happening, but it depends what you're about to do next. Are these values that you care about and need in order to do honest analysis? Or are they things that just don't make sense for what you're about to do and they would make the results not make sense? Depends what you're about to do. Again, I heard myself say, I think it was in week one, if you can outsource this to an LLM, you deserve to be outsourced to an LLM. There's a human judgment call that has to be made about this. And well, I don't think any large language model pressing autocomplete to finish a sentence is going to get there. That being said, there are a few things that are reasonably common. Do you have valid data, right? Just, is there a straight missing value? Or, the thing back here that was no clue. Well, no clue, not a valid zip code, looks nothing like a zip code, fine. And then there's the like semantic validity where I might have a field that is length, and that's a numeric thing, and -10 is a number. No like natural data reading process or whatever is going to exclude -10 as a valid length. But I don't have a ruler. If I had a ruler, it does not have a -10 on it, right? -10 is not a valid length of anything. It's not how length works. This is this matches the format of a date. It looks date-like, but I know February does not have a 31st day. I know that Canadian phone numbers do not have 555 in that position. Those numbers are reserved for, I don't know, whatever, use on TV or something. I have a judgment call to make on those, or I have to understand my data. I guess in these examples, I have to understand my data well enough to know that this doesn't make sense and is not a value that I should keep around. Maybe I replace it with not a number. Maybe I throw that whole row away. Again, depends what's going on here. One of the ways data can be bad is an outlier. And an outlier in general is something that's different than the rest of the data set. There's no great rule on that. It's often something like how many standard deviations away from the mean. So like what I have here is, like, I think it's obvious. There can be no question here. What I have is data that's drawn from a normal distribution centered at 0 with standard deviation of 1, 1,000 data points. That just is what that is. And if I do the same thing over here, I find out I have to import the things. So what I expect is that, yeah, I expect the mean to be close to 0, the standard deviation to be close to 1, because, yeah, what else would it be? But in this data set, notably, I have a max value of 4.1. That is pretty far from the mean, right? That's 4 standard deviations away from the mean. Now, maybe I got unlucky that time. But, it'll happen. That's how normal distributions work. Yeah, okay. So I got, in some sense, a little bit unlucky this time I ran the code, and I promise it was real. I really did run the code. I really did get these values. So this data point that's hanging out here 4 standard deviations away from the mean is an outlier, right? Like, there's no question, nobody's definition of outlier would not include that. So what do I do with the outliers is the question for the moment. And if your instinct is throw them away, I challenge you that that makes no sense, because this data, absolutely no question, this data point was a valid data point sampled from the distribution that I'm claiming it is. So it makes absolutely no sense to throw this away just because it's an outlier. It just happens to be a weird data point. Weird data points are allowed. This is like, you know, if you're measuring people's heights, like, this seems to be the example I use in lectures just because it's dumb and easy, right? Like, we have some question about like, oh, how tall are people? Well, get your measuring tape and go start measuring people. Like, it could be that like Shaquille O'Neal happens to walk by and let you measure his height. It's going to look like this, right? It's going to be way far out on the thing. It's going to be a crazy outlier. Well, you tell him his height is not a valid height for a human to have, right? Like, it's a true measurement. Now, that being said, if I record somebody's height and I write down 16 feet, or what is that, about 5 meters, well, that's definitely an outlier. Same way Shaquille O'Neal is an outlier. That one's probably an error, right? I know people aren't that tall, but there's a judgment call here and understanding the data that's necessary to decide which one you're going to do. People think, by the way, like, I feel like at your point in your like you know, data journey, the way that data can be wrong and is wrong in reality, I don't think you're up to speed. Like, literally, there's a story among friends of mine who are field biologists, like have biology degrees, and we're out there measuring stuff literally in a field. We lost that data because literally he wrote it on his arm and washed his arm before copying it into the notebook because he forgot the notebook in the truck. Or a McDonald's wrapper. Like, both of these are things that happened to actual people I know. So sometimes the data is just a genuine error, or the McDonald's wrapper was not high enough fidelity to capture whatever is being measured. That happens. Sometimes data is just weird because the thing was weird. There was one really big or really small or really fast. Like, that just happens. And you have to decide as a, frankly, human. Okay, so in my like example madness here, obviously not real data, but I might, like, this is reasonable, right? Like, I have some like smart house setup. I don't, because I like light switches just fine, but I have some smart house setup. I want to decide, like, oh, when do you turn the air conditioning on, or should I open the window, or, you know, whatever smart homes do. This seems like a reasonable measurement. It feels warmer than that in this room right now, but you know. Okay, this is also a valid measurement of air temperature. It's just not the temperature I care about when I'm thinking about the air conditioner or opening a window. This is an outlier. It's weird data, and I have to make a judgment call about whether this is valid. You know, this, like, if I measure this, and like this is probably a pretty close, it's a lot higher than the rest of the temperatures in the house. Maybe that's because there's a computer below it that's kind of gently heating it. Maybe because my hand has been sitting on the desk. Maybe it's just because it's really hot in this room because I'm recording a lecture and my lights are on and it's hot. Don't know. Have to think about it. Have to decide, do I trust my sensor? What am I measuring? What do I care about? So I guess maybe I should distinguish here, like, even if you have a really nice, clear definition of what an outlier is, outlier and bad data point are definitely not synonymous. Being an outlier does not mean you should throw it away. Being an outlier is just this data point is kind of a little weird. And the thing you should do if you want to really understand your data is draw a plot. And in exercise 2, you're going to start drawing some plots. Human eyes are good at seeing things in visualizations if you choose the right visualization and you draw it right. And then you can kind of start figuring out what's going on. So in that exercise 2, one of the things I had to do was just, okay, it was remove, I think I said 25, like remove things that have a score greater than 25. And I just said that. I just made up that rule and gave it to you. And I bet you, what are we at here? Will, sorry, want to get the verb tense right there. You will probably just do that because I said to. And yeah, well, it's an assignment, so of course you will. But maybe you should have or should look at these data points. This number, so how did I decide? Like, why did I decide, I guess? Where did this number 25 come from? I looked at these things that were greater than 25 and decided they weren't real. This dog, again, this is how cute is this dog on a scale to 10? This dog was given 1776 out of 10, 1776 out of 10. It's a dog wearing like stars and stripes, and 1776 is the US independence, right? So this is not a real number. It's a joke label that just happens to look like a number to a regular expression. This is a 666 devil Halloween costume job. This is a 420 dog. I forget what the one something is, but they're clearly not real ratings. They're numbers, they're data points, they're outliers. That's all fine. You're allowed to be an outlier. What you're not allowed to be is an invalid data point that doesn't mean anything. So for this one, you look at the 420 dog and you think, okay, is that dog 42 times cuter than the dog that got rated 10? No, that's not what that number means. It's actually not a valid measurement on this data set. We'll throw it away. And so the number 25 was just the one I picked to give you on the assignment. You would have got a plot something like this. I don't remember. This might be an older version of the data set or something. We still have some outliers, right? There's still these weirdos down here that are 0 and 1 out of 10. I think like one of them's a skunk or something like that. Like, okay, but now you ask yourself, are these valid data points? And well, again, for the purposes of exercise 2, yes, just because I told you they were. I didn't tell you to throw them away. But if you were going to do real analysis on this data and come to conclusions about this Twitter account, or I'm sure he's now on Threads, etc., you got a call, right? You have to decide, do I want to keep them because they make sense and are valid measurements, or do I throw them away because they're invalid measurements? It depends what you're doing. And maybe it's like, if the question is this account, suffering from grade inflation over time, maybe you keep them because they were ratings given. If the question is, are the ratings of dogs getting higher over time, you throw them away because they're not ratings of dogs. It can be subtle, and it's not obvious what you should do there. So this was 2-dimensional data, so the scatter plot feels like it makes a lot of sense. 1-dimensional data, I mean, you can do a box plot, right? It certainly tells you like, okay, this is all my data, the like 90th percentile or whatever the box and whiskers include, is all squished down to 1 pixel, and I have this data point stretching my graph out like crazy. I still have some data points here that are outliers, but again, they're not as bad. I can kind of see what's happening. I can think about those outliers now. I can identify them and think about them. I would probably go for a histogram way more likely than a box plot myself. Yeah, that seems reasonable. I can tell there's outliers here because it's stretching the scale of my graph. There's like, 1 or 2 data points, tiny little bars in the histogram there. Sure. So there's definitely some values that aren't valid. Again, the 1776 dog is not 176.6 times cuter than the other dogs. So we removed it. You've got a judgment call to make. You've got to look at the data and understand the data. again, maybe it's a valid thing, right? Maybe that was just the cutest dog ever, and for some reason it actually is 42 times cuter than the 10 out of 10 dogs. We chose this one. It's like, this was just not a valid measurement of dog cuteness, so we throw it. We could have, if we wanted to keep the row, we could have replaced the rating with not a number and kept the rest of the row. That wouldn't have done anything useful for what we did in the exercise. Maybe, depending on the data set, what you want to do is impute. Imputing is calculating a replacement value for something that's missing, or that's missing because you just removed it. If this makes you suspicious, it should, right? This is a really sketchy thing to do, to just sort of take a data point and say, I'm going to make up a number and I'm going to put it in my data set here, and then I'm going to use that number for some analysis I do later. That is sketchy. Because you're just introducing fake data and then pretending it's real and pretending you're coming to real conclusions about it. But it can depend, and it can make sense. In general, the thing that would be done here is usually mean substitution. Often this is done for like machine learning training data, where it's just like, I need a number because I have to have a number that goes there in order to continue the calculation. But I want it to be like the most boring number possible so it doesn't throw off the rest of my machine learning training process. And that would be just put the average in there. It doesn't mean it's a real number. You're just hoping that having a number there that's kind of as boring as possible will let your machine learning training continue. Is that a valid thing to do? It depends what you're doing. If you have like time series-y kind of stuff, like things that go, you have a measurement every second or something, like the example I'm about to show, maybe effectively doing a lowest smoothing and taking the lowest output at that X value makes sense. Kind of depends what's going on. So I think if I give an example like this, so again, we imagine this is the grad student sitting in the truck, watching the thing happening, watching the birds come and go or whatever they were doing. It can be like, you can have this kind of thing where they just forgot to write the thing down. So that's a missing value. I think we can all guess what number should go in that spot. But, well, if I did a lowest smoothing of this value, but converted to a number, well, I would probably get 1425 here as the output. And that's probably a really sensible thing to put there. And it lets me save this row. This row, this row is where like interesting things happen, right? X goes from like the teens to the 20s, and the Y goes from the 400s down to the 200s. This row is really cool and interesting. I kind of don't want to throw it away. I'm pretty confident I can guess what number should go there. And if I call it imputing, I guess I'm being honest about what that process is. Because yeah, I think the time is probably not the important thing. I can probably make a good guess and just carry on. I probably would not want to impute this Y value. That's really weird to just sort of take the average of the things on either side and shove it in there. Maybe that's not right. Maybe that's completely a completely fake trend that I'm introducing. I have a judgment call. So maybe I want to leave it. Maybe the fact that there is a missing value there is what's interesting. Maybe I have some sensor that, it measures the temperature in the room or whatever. It measures the load, like the system load on my server or something like that. And it fails when things get too hot, or when the server is completely overwhelmed by everything else. My thing that records, that does the monitoring fails, and I don't record the server load when the server load is completely unreasonable or something like that. I can imagine these things happening, and then it's all of a sudden it's not the number I care about, it's whether or not the number was missing is actually the interesting fact. That also can happen. And again, like, depends, right? Like, maybe the number here is missing because the grad student sitting in the truck was so excited that the thing finally happened, they forgot to write down the time. And so the missing times are the interesting moments. Maybe. Again, I know I have to make up a pretty weird story to make that make sense, but it can happen. All right, mentally insert the noise filtering slides here, right? So noise filtering is one of the things you can do to clean up your data. It's if there's noise, sensor noise, measurement noise, whatever it is, and that noise is actually a problem, right? You don't have to noise filter just because your curve isn't perfectly smooth. You have to noise filter if the noise is actually throwing off whatever other analysis you're doing. But maybe you have to. Maybe you should think about it. Maybe you should have the technique in your pocket. Okay. Another data cleaning thing. Entity resolution, record linkage, sure. Like, again, entity resolution is a term that sticks in my head. This is, are there multiple values, usually strings, that are sort of labels of things that actually refer to different strings but refer to the same concept? And like, I think if I say this, you will say, oh, right, that, right? This string and this string both refer to me sometimes. I am one person, you know, there are other people that share this name, but how do you unify those? This is a bit of a hot button for me. I don't care. Like Gregory, I don't really care personally. But SFU has this not quite policy that we should use the preferred name for, I think, obvious and good reasons. And then the people that email me and talk about this policy, the email says Gregory, which is my legal name, and I actually entered this as my preferred name in the system just to see. I don't care, but I do care that we're doing the right thing with people's names, and we're not. Courses does. Courses uses preferred name everywhere with a very small number of exceptions. Other systems at the university do the wrong thing anyway. But of course, this is okay because we don't identify people by name. Your mark on the quiz doesn't get beside your name in the grade book because we matched your name. It gets there because we matched your student number. Because these strings are weird, right? Like, I looked these up earlier. You know, I could buy this thing from Amazon. I could buy this thing from Canada Computers. Are they the same thing? Like, the strings that identify them are radically different strings. And okay, by I, as a human, I understand that 9850X3D is the thing that matters, right? That number matches, so these are the same product. I can compare the prices. But what if I want to do it automatically, right? Like, what could I do if I wanted to do a PC part picker type thing to convince myself that this price and this price can be compared? Are they really the same product or not? Well, that's entity resolution. You hope that you have something to break that apart so you don't have to. And again, for us, it's like student number, right? Like, it's not like we think of, well, it's not like I think of you as faceless numbers. What the upper administration does, who knows? And how they feel. I am more of an employee number than I am person in many contexts, I'm sure. But having that number lets us know who this person is with no ambiguity, and it's not hard. We don't have to guess like, oh, are these names similar enough? Is this a short form for that name? No, student number, done. On those pages, there is like the Canada Computer part number name contains this string. Somewhere down here, I found it earlier, also contains that string. Is that enough? Like, like, I don't see exactly this string anywhere, but I do see this one. So if I have that, like if I have some like reliable, like manufacturer part number that I can use to unify things, hopefully that, right? Maybe I'm just dealing with something that's like typos kind of stuff. Like, people tried to type this string and they just missed a couple characters or whatever. Well, then there's some approximate string matching algorithms that will get you close. In exercise something 3 or 4, you're doing some effectively entity resolution with geography, which is just like whichever thing is closest, we'll call those the same thing because the latitude and longitudes are not exactly the same, but they're close because the things are close. Or again, I have a store that I peel some stuff out of the Google Maps API or whatever, and I find out, okay, there's 2 things that are called Walmart and they're only 500 meters apart. It's probably the same thing, right? It's probably the same Walmart, but that's not necessarily the same Starbucks. I can think of, well, less than 500 meters from me, there are 2 Starbucks. Okay, so that heuristic is not going to work, depending what you're talking about. But if I know about my data, I can start to make reasonable guesses here. Okay. Let's talk about, again, one of the things that can just come up when dealing with data, cleaning data, specifically strings. Because of course, strings are what happens, after the user enters something, or if I extract a string, I extract the model or whatever from a web page, fundamentally that's going to be a string in my programming language. So what do I do with that? Or at least one of the things I can do with that, and again, a tool that I think should be in your toolbox and you should be at least a little bit comfortable with, are regular expressions. So fundamentally here, the verb that goes with a regular expression is match. I have a pattern and I want to know, does this string match the pattern or not? So that's sort of the first step to do. And I guess if it matches, like, how does it match? Which parts of the string match which parts of the pattern? So the game that I'm playing here is I'm imagining some tweets that I guess I've cleaned a little bit already, right? I've taken some stuff maybe from the Twitter API. I've extracted just the text of the tweets, and maybe there's some other columns that I'm not showing in the slide or whatever, something like that. Okay, and then I have this pattern. So I'm imagining some task here, like, oh, I'm watching tweets to sort of see if people are expressing a party preference or a voting intention or whatever. So the pattern that I've given here is, well, it's literally the characters VOT and then either an E or an ING. So either vote, this is either vote or voting, for, and then something. Not every string matches that pattern, right? This string does not match that pattern, but these other ones do. And I guess what I've said here in Python syntax, and maybe I'll just do it. So I've got this data, this string column, and I'm just going to do that much because I don't think it's obvious what this stuff is doing. Okay. When I have parentheses in a regular expression, it's doing 2 things. Specifically what it's doing, well, it's doing both the usual thing parentheses do in a programming language, which is like hold things together, right? Like if I just want to do, I don't know, whatever arithmetic, that kind of thing, right? Like these parentheses are doing that thing that they do in math class. And that's what I'm doing with these ones in this example. I just want either this one character or those 3 characters. I just want that sub expression to be held together. So parentheses do that. The other thing parentheses do is mark parts of the string that I want to capture. So what I'm saying on this one is I care about, like, so the dot star is anything, and we'll come back to why. But so I'm going to have either vote or voting space for space. And then whatever comes after that, I care about this. I want that substring, and the parentheses also do that. So the pandas str.extract on a column series. This function takes a regular expression and gives me for each row that matches, it gives me the match groups. So the not a number here is it didn't match. This pattern does not match that string, so I have no way to do it. But these other ones are, okay, what string matched this? Which string matched this? So the thing is, I don't care about this one. I could, like, obviously I could look at it if I was interested in it, but I don't care. That ended up being column 0 of the output of this thing. And then I have a column 1 that's the part I do care about, the second match group. So this is a column, a series that I can get behind. This is the one I need, the one I care about. So maybe what I would actually do here is that I'd probably do that. Okay, well, so that's not a political party, but it gives me some indication of what's going on there. Okay, so maybe I should rename that. I should call it preference. And now it's there twice because I run my code in a weird order, but okay. I have no idea how much is in this notebook now, but there we go. And also normally, I was going to say normal, I'd spell preference, right? But that's not true at all. Okay. So this is the pandas way to spell this concept. This str.extract is with this regular expression, give me all the things that match and as many columns as you need, and I'll pick the columns I care about. The Python regular expression way to do this is with a match group, or to express it as a match group. So this is, if it matches at all, then I know there will be a group 2 because the Python regular expression library numbers from 1. So it's what matched the entire thing is group 0, and then group 1 and group 2. I care about group 2 for this game. Also, perfectly fine. I can do this. What else should I say here? In the Python regular expression library, there are 2 functions, methods on that regular expression object, match and search. I get this wrong almost exactly 50% of the time. But when I stop and think about it, match looks at the start of the string, search looks anywhere in the string. So I don't care where in the string, if they start at the end or whatever, they say voting for X. So it's a search. If I cared that VOT was the start, I would use the method match here. Result object, same thing. It returns an object that contains all the stuff if it worked, and then a null if it didn't. Okay, I haven't actually talked about what a regular expression is, or I haven't talked about like how to express yourself with that pattern, but those are the tools. And again, I would probably prefer to do the Python or the pandas thing if I could, just because it's, I don't know, a little easier. I get to stay in pandas land. It's probably faster. Okay. Bunch of stuff that's happening here. This raw string, like I had done this here, right? Like this string is a normal Python string as you know it. This R like prefix to the string, and it can be on either single quotes or double quotes, same. That R prefix means it's a raw string. In a raw string, the backslash is not special. In a normal Python string, the backslash does a special thing. Backslash n is a new line character. Backslash t is a tab character. Those kinds of things are normal Python stuff, and also in C and other languages. In Python, at least, and Rust, the R means raw string, and then that's just 2 characters, a backslash and an n. So backslashes come up a lot in regular expressions, so my fingers just kind of naturally put that R there, even though I don't think I need them in this case. Yeah, I did this ahead of time. Like compiling the regular expression into a regular expression object is not free. So I want to do this once and then use my regular expression object many times. And probably what I want to do with it, at least for a Python regular expression, is either match or search to see if I can find the thing or not. And with a pattern like this, if it was successful, it will evaluate as true-ish. So it's all match objects evaluate to true. The none object that it returns would evaluate as false in Python. Okay, within this pattern, so this is like for the stuff that's going on in this context. Most characters, like if I don't say anything else about the character, it matches itself. So like VOT match literally those three characters. A dot matches anything. If I don't want that special behavior, I can do that. And now I definitely need this raw string situation because that backslash is not Python syntax, it's a regular expression syntax, if that makes sense. That would actually match a period. The star modifies the thing before it and matches some number of them. 0 is allowed. A plus sign is the same thing, but I have to have at least one of them. The question mark is it might be there, might not be there. Start or end of string. This is any one of those characters. So this is either an A or a B or a dot. Several of them because of the plus sign. Much more useful are things like digits and spaces. Because, you know, if I expect there to be a number, well, probably that's going to be some digits. This is a lot like a regular expression for an integer, but not quite. Pretty close, at least. You know, if I know there's some number of spaces that separate things, that might be backslash s plus. That will be one or more spaces. More realistic example. Like this is probably the way something like this is going to would come up in like a data cleaning or maybe an ETL kind of context. I have something like the log files from a web server. And if you've not logged, like this is, I mean, I've shortened it just so it fits on a slide, but this is kind of what they look like, right? Like every time somebody requests something from a web server, the web server appends a line to a file that looks kind of like this. And it's something like, what IP address made the request? What was the request line? What was the response code? And that's, again, it's usually, I'm actually finding that hard to look at because they're usually much, much longer than that, but we'll go with that. What I care about is not this string, right? Like this line is obviously a string. What I care about is like, what's the number in this position in the string? So a totally reasonable way to use a regular expression. So I have a raw string that describes the thing I've got, and I have a regular expression here that is a little broader than it needs to be, but would capture any IPv4 address, which is what it looks like I've got here. So this is one or more digits. I know it can't actually be more than 3 digits, but one or more dot number dot number dot number. So yeah, four numbers separated by periods is what that would capture. And then it looks like I have a space, quote, get space, and then the path part of the URL probably. So again, I could go to the spec and I could figure out exactly what the syntax is for a path and a URL, or I can just say, you know what, I know they don't have spaces in them. I know URLs are not allowed to have spaces, and I know how to express non-space character in a regular expression. So frankly, that is exactly what I would do there. And then it looks like, again, I have space HTTP slash, so literally those characters, and then digit dot digit, 1.0, 1.1, and then again, like I'm ending the world here with this thing. I have been a little bit more precise in my regular expression. I've said, we will have the start of the line here. We will have the end of the line after that. If things don't meet this pattern, they won't match. And then I would go for it. Go through each one of these things. And I might, yeah, this is probably how I'd write my code. I would expect that usually, like I think every line in the file is going to match this pattern, but I'm not just going to go for it. I want to know as fast as possible if it doesn't. I want to fail if it doesn't match, and then I can process the match. So yeah, have I been overly cautious here? Maybe this could be an IPv6. Maybe it could be a domain name. I don't know. Maybe HTTP progresses to version 10, and then I would have more than one digit in that spot. I should be careful about that. Maybe sometimes there's an extra thing on the end of the line. I should be careful about that. But that's kind of what this is doing, right? Like if there's bad data or data that does not match my regular expression, I want to know about it. I want to fix it. And then I don't actually just want to know yes. Like this is fundamentally just telling me yes or no. Here I've added these parentheses, and the parentheses are saying I would like to extract the substring that matches here, here, and here. So I'm capturing the IP address and the path and the response code. Again, Python syntax counts from 1 on those match groups. Panda syntax, it counts from 0 just because it does. So you end up with this, right? And I don't know, like whatever you're doing, like whatever it is you want to do with this data, that's another question. Maybe I want to convert that to an integer. Maybe I want to convert that to like an IP address object or something. Who knows? But I can extract stuff from reasonably nicely regular strings this way. So regular expressions are kind of a double-edged sword. You can do a lot with regular expressions. You can also trick yourself into believing that some string task can be done with a regular expression and be just wrong about that. They're the right tool for the right job. They're not the right tool for the wrong job. So be a little cautious. So I think you should, both for this course and for your life, know at least some basic regular expression stuff. It's too valuable to not have somewhere in the back of your mind that's like, oh wait, I have a string that has this pattern to it. I want to get the pieces out of the pattern. Very often a regular expression can help you there. Okay, I've got a few minutes left. That's good. All right. So that is what I'm going to say, at least in the lecture, about data cleaning. And it's completely non-representative of the amount of time one typically spends doing data cleaning as a data scientist, but it is what it is. Again, there'll be a couple of weekly exercises where you do some of these things. Again, a little entity resolution, a little string manipulation. In general, it's just uglier than that. In a way that, again, I don't think I can express until you've had to clean real data with all the horrors that happen in real data. But you'll get some sense of it. Some of you, at least, will have some appropriately horrible data in the project. But let's move on. And get to at least some of how do we get, now that we have data that we can work with and makes a little bit of sense, how can we get answers out of it? Well, first we need to have that data, but, well, there's definitely more than one thing that counts as data analysis. Sometimes the data analysis is just like looking at a really good plot and telling, saying some words about the data. That's perfectly valid, right? To not have sort of hardcore data analysis and to just skip to like, okay, I'm going to explain what's going on here step, depending on the goals and what you need to do. The thing that we're going to do next is do inferential stats. So you have a statistics prerequisite, and I don't know what happens in the stats courses. Like, we created this course. I'm like, there should be a stats prerequisite because, they need to know the stats to do the data science. And then students come along and I don't know what the hell is going on in stats courses. But anyway, we'll do some review. Because experience tells me most computer science students are hanging out over towards effectively no statistical knowledge whatsoever. I don't need you to be over here. Hooray if you are. If you're a data science major and a stats major, and I know you're out there, I'm sorry I generalize this class as CS majors. The rest of you all, sup, I'm glad you're here. But I don't need you to be a statistician for this course. Or like, if you're leaving this and you're going to not be a, real, like you're not, your job title is not going to be data scientist, cool. You don't need a huge amount of stats. You probably need more than you would have otherwise, frankly. I want to move you over a little bit, enough that you can reasonably do something with statistics without shooting yourself in the foot and actually come to valid conclusions. That's the goal here. Don't pretend to be a statistics expert because of anything I tell you, because I wouldn't. Like, if there was really serious consequences on the line, I would put up my hand and say, yeah, but I'm not a statistician. I don't think I can do this, in a fair and honest way. Go find a biostatistician or whatever when the time comes. But let's do some review. Okay. Yeah, doing great. Okay, maybe this slide is for me, because I know when I say data, I'm usually thinking of a number. And this is a character flaw on my part. But okay, these are different, right? Like these things that you can say, like I can look at, 18 and 36, and I can say one of those is twice as big as the other one. Those are numeric values, they're quantitative. There's also these things that are, again, I think like your letter grades are probably a really good example. They come in an order. We know that A+ is greater than A, which is greater than A-. We don't know how much. It's not like an A+ is 38% better than an A or whatever. That being said, the thought that a lot of you just had was, yeah, I know exactly how much it is, because the first thing we do when we give you letter grades is then convert it to a grade point that is numeric, because we want to be able to average them and stuff. But I will assert that the letter grades on their own are just ordinal. They have an order, but not a magnitude. The same thing with what is it? Is the Likert scale? The strongly satisfied, strongly dissatisfied scale, like that 5-step thing, whatever words you use for it. Also ordinal, not quantitative. Nominal values, also perfectly good things. These like categories or something, which color, which city, which side of the experiment were you on? Also, perfectly good data. And I know deep in my heart when I say data, what I'm picturing is 4.2. I shouldn't do that. I should be a better data scientist. All right, this is a good spot to stop rather than to get into this. So, yeah, we're starting into the sort of meat of the course here, analyzing data. We will continue to do this for a few weeks. I don't know. See you on Friday. See you in the next lecture. Bye all.